what if the entire universe, I mean, all of it, from the tiniest quantum particles all the way up to gravity itself, what if it all boils down to just one simple shape, but in motion? It's a pretty wild idea, right? Well, today we're diving into something called supersymmetric geometric quantum mechanics. Yeah, it's a mouthful, so we're just going to call it the geometry of everything. And it all kicks off with something you definitely remember from math class, the Pythagorean theorem. A squared plus b squared equals c squared. But what if that rule we used for flat, boring triangles on a blackboard is, well, what if it's actually the instruction manual for the entire universe? Okay, so here's how we're going to tackle this. We'll start with that old geometric rule, then look at the huge problem that's been bugging physicists for a century. After that, we'll see what happens when we put that triangle in motion, explore the spin of reality, and even ask if this could be the missing piece to Einstein's theories. Finally, we'll zoom out and see what a geometric universe really looks like.
All right, first things first, let's get back to basics with something we all get, the perfect static world of Pythagoras.
You know, for thousands of years, this equation has been rock solid. It's a symbol of pure certainty. It works perfectly for a triangle sitting still on a flat piece of paper. It's timeless, it's reliable, and it's completely, totally static. That triangle isn't going anywhere. But here's the thing, our universe isn't static at all, is it? It moves, it changes, it evolves. So to see why we might need a triangle that moves, we have to talk about the biggest headache in all of physics.
So why would anyone take that perfect, simple triangle and mess with it? Well, it's because modern physics has a huge problem, a massive split right down the middle between the universe of the really, really big and the universe of the incredibly small.
Okay, so on one team, you've got Einstein's general relativity. This is the master theory for everything big, planets, stars, galaxies. It describes gravity as this beautiful, smooth, curving fabric of space-time. Then, on the other team, you've got quantum mechanics. This is the rule book for the tiny, bizarre world of particles. And here's the catch. Both theories work, like unbelievably well, but they absolutely hate each other. They use totally different math. They have totally different rules. If you try to use them together, say to describe a black hole, the math just breaks. It spits out nonsense. And that's the wall physicists have been banging their heads against for 100 years.
And that's where this new idea comes in. It asks a simple question. What if we take that static triangle and make it dynamic? What if it spins?
And here it is. This is the Aetheron theorem. Now it looks familiar, right? But it's gotten a serious upgrade. Those letters, A, B, and C, they're not lengths anymore. They don't measure distance. Instead, they represent the fundamental building blocks of reality itself, matter, energy, and the unified state that contains them both. And the key is, they are all locked together in a constant spinning dance.
So where is all this spinning happening? Well, the theory proposes a kind of fundamental medium for the universe called the Aetheron. The best way to think about it is this. Space isn't an empty box. It's more like an ocean, a vast invisible fluid. And this Aetheron ocean is always in motion, always swirling. So in this picture, a particle or a wave of energy isn't a thing floating in the ocean. It is the ocean, just a temporary pattern, like a whirlpool or a wave made of the ocean itself. Let's take a closer look at what these new sides of the triangle actually mean. So that hypotenuse alpha, that's the whole shebang. It's the total amount of rotation in the system. Now, imagine this spinning thing casts a shadow on two different walls at the same time. The shadow on one wall, that's mu, and that's what we see as matter, physical stuff. The shadow on the other wall, that's E-rot, and that's what we experience as energy or force. The crucial bit is they're not two different things. They're just two different views, two perpendicular projections of the exact same single rotation.
Okay, so if reality is just geometry spinning around, how in the world does that create, well, us? How does it make matter and all the things we see?
Well, according to this idea, a particle isn't some tiny little ball. Nope, it's more like a stable, self-perpetuating knot of rotation. Think of it as a really persistent whirlpool in that Aetheron ocean we talked about. And the specific way that whirlpool twists and spins is what gives the particle all its properties, its mass, its charge, everything. Okay, now this is where things get really, really cool. And a little weird. In quantum physics, we already know that for a particle like an electron to get back to its original state, it has to rotate 720 degrees. Not 360, but 720. That's 2 full rotations. It's a known property called spin 1/2. Now, this theory says that's not just some strange math rule. It's a literal physical requirement. For a knot to be stable, it has to complete 2 full turns. So how does this 720-degree rotation actually work? The idea is that it happens in 4 distinct 180-degree flips. Imagine with each flip, the particle shows a different face to the universe. So flip 1, that sets its spin. Flip 2, that reveals its electric charge. Flip 3, this is the one that generates its gravitational pull. And finally, flip 4 brings it right back to the start, locking it all in place as a stable piece of matter.
And this visual right here shows it perfectly. Just look. You start at the top, at 0 degrees. Now follow it around for 1 full rotation to 360 degrees. See how it's now upside down? It's not back where it started. It's only after it goes another full 360 degrees, for a grand total of 720, that it finally returns to its original position. That, right there, is supposedly the geometric secret to why matter is stable at all.
All right, this is all fascinating for the quantum world, but if it's really a theory of everything, it has to connect back to Einstein and gravity. And the bridge between them? Well, it turns out to be a very specific and kind of mysterious number.
8 pi. That's it. Just 8 pi. It might not look like much, but in physics, this number is a giant. It's the linchpin that holds the world of the big and the world of the small together.
See, in Einstein's famous equations for general relativity, 8 pi is the magic number. It's the conversion factor that tells space-time exactly how much to bend when there's matter or energy around. But here's the thing. Einstein basically had to just plug it in. It made the math match reality, but he never knew why. Why 8 pi? Why not 7 or 12 pi? It was just a number that worked.
Well, this geometric theory claims to have the answer. It says 8 pi isn't random at all. Okay, remember that 720 degrees spin that stable matter has to do? Let's talk in radians for a second. 720 degrees is the same as 4 pi. So the theory goes that a full, complete interaction in the universe requires 2 of these particles to link up, 2 of these 4 pi spin cycles coupled together. And what's 4 pi plus another 4 pi? It's 8 pi. So the idea here is absolutely huge. That mysterious number Einstein needed to describe gravity on the cosmic scale is actually just the geometric fingerprint of a complete quantum spin on the tiniest scale. The small is literally dictating the rules for the large. Now that is a bridge between the two worlds.
So let's step back for a second. If this is even remotely on the right track, it completely changes how we should look at, well, everything.
In this new picture, the 4 fundamental forces of nature we've always talked about, they aren't separate forces, they're just different notes in the same cosmic song, all played by this one geometric instrument. So gravity, that's just the deep, slow bending of the whole structure. Electromagnetism, that's a faster vibration, an oscillation. And a super strong nuclear forces, those are just really tight, localized twists in the geometry. It's all just one thing expressing itself in different ways.
And that really brings us to this quote from the theory's author, Aaron Bassemi. He says, SGQM is not merely a new theory, it is a new way of perceiving reality itself. And that really hits the nail on the head. The invitation here is to stop thinking about stuff, particles, fields, forces, and start thinking about pure shape in motion.
And that leaves us with one last, big question to chew on. For the last 100 years, our approach to finding the secrets of the universe has been to smash things together harder and harder, looking for smaller and smaller bits. But what if that's the wrong approach entirely? What if the deepest secret isn't a tinier particle, but a simpler pattern? One that's been hiding in plain sight this whole time, in the simple, elegant geometry of it all.